Humanity has long dreamed of being able to fly. Through the courage and innovation of pioneers such as Otto Lilienthal and the Wright brothers, this dream has become a reality. Now you're going to learn about what lay behind these visionary ideas and about the flying machines of today. On account of the Earth's gravity, all objects are attracted towards the Earth's center by a force which can be measured as weight.
Discovery Houston. Nice to be in orbit.
This is also true for airplanes. If no wind blows, the only force acting on an airplane is its weight.
When a gas or liquid flows through a contraction in which the flow rate flow does not change in time, then the same fluid mass passes through any cross-section. When the cross-section is large, the fluid velocity is small. When the fluid must pass through narrower sections, its velocity increases, such that the same mass passes through. This increase in velocity gives rise to a decrease in pressure. This is particularly true of fluids of constant density. The paths along which the particles move are called streamlines. Here you can see streamlines plotted at equal distances to each other. What holds true for the entire cross-sectional area must also be true for the area between two streamlines. If the cross-sectional area is relatively large, the velocity will be small. On the other hand, when the streamlines get closer together, the velocity is higher.
These relations can now be transferred from the converging-diverging channel to flow over objects. Here you can see an image of a flow around an airfoil, in which one sees areas in the flow where the distances between adjacent streamlines become smaller, and others in which those distances get larger. This means that the velocity in the first areas increases, while in the second it decreases. In this respect, it is irrelevant whether flow passes over an object, for example in a wind tunnel, or the object moves forward through the air as an airplane does.
It is known that an increase in velocity is related to a pressure decrease. Consequently, when the object velocity increases beyond the oncoming flow velocity, then the pressure around the object is lower than the surrounding pressure. At locations with closely spaced streamlines, where the velocity is relatively large, the pressure is relatively low. By contrast, when the velocity is lowered with respect to the oncoming flow, then the pressure increases compared with the ambient. When streamlines are far apart, the velocity becomes lower and the pressure higher.
Forces are vectors which are always 90 degrees to the surface upon which they act. When equal forces act at the same line of influence and in opposite directions, their relative effect is cancelled. On airfoils and airplane wings, pressure on the upper surface, especially near the nose, is very low. When the ambient pressure acts on the lower surface of the wing, the balance of forces is destroyed and a resulting force pointing upwards remains. This effect is pronounced by the fact that the velocity on the lower wing surface is made to be as small as possible, and hence the pressure acting locally on the lower wing surface is higher than ambient. As a consequence, a resultant force arises. It is called lift.
Calculation of lift becomes increasingly accurate when the surfaces panels on which pressure locally acts are made ever smaller. When an airplane is constructed properly, lift exceeds weight such that lift not only compensates for the airplane weight, but is also capable of lifting the airplane in the air. The forces in question are very large. For example, for an A380, they lift up to 560 tons.
At the same time that lift is created, there is also a redirection of the flow downwards. This phenomenon is called downwash and is also to be found in flow through a curved duct. Seen macroscopically, lift is created through the change in direction of the flow, which results in the generation of forces F1 and F2. The resultant force can be decomposed into a force perpendicular to the incoming flow, lift, and aligned to it, drag. When an airplane flies slightly above a dense blanket of cloud, the downwash can clearly be seen together with the vortices produced at the tips of the wings.
It is a misconception that wind molecules that separate at the airfoil nose and flow above and below the airfoil respectively will meet again at the airfoil trailing edge. Air molecules at the upper surface of the wing are substantially faster than those which fly over the lower surface.
Friction between the plane and the air that flows around it, as well as friction in the air itself, gives rise to a force which acts in the opposite direction of motion. This is called drag. At low speeds, drag is roughly proportional to the velocity, and at higher speeds, to the square of the velocity by which the object moves through the fluid. Work needs to be done in order to overcome the effect of drag. Two different kinds of drag have to be distinguished: skin friction drag and pressure drag. Skin friction drag directly originates from the friction between the air and an object. As a consequence, an additional pressure drop is encountered along the object's skin, and in conjunction with this, an additional drag occurs. This kind of drag is strongly influenced by the form of the object and its position in respect to the airflow.
Drag increases substantially when separation occurs in the flow. Separation is made visible by particles which do not flow along the surface of the object anymore, but depart from it, generating areas of backward-flowing fluid. Flow separation can occur as a result of an increasing pressure along the flow direction anywhere along the airplane surface. However, separation becomes critical when it occurs on the wings, because it not only increases drag, but it also decreases lift. The danger for the airplane increases when the separation zone becomes increasingly larger. In the limit, the lifting surface, the wing, does not produce lift anymore and the airplane stalls, meaning it produces no lift anymore. During takeoff, the airplane accelerates, which produces an additional drag force.
In order to overcome drag, the airplane needs propulsion force, both during takeoff and during level flight. Propulsion acts in the direction of the airplane motion, which is in the opposite direction to drag. Propulsion is obtained from propellers or jet engines. A propeller, in principle, is constructed of components having the shape of and working in the same manner as airfoils, although when it comes to propeller components, one speaks of blades rather than airfoils. Rotation gives rise to a relative air motion around each blade and, again, a difference in air pressure on either side of the propeller blade gives rise to a force which drives the airplane forward. This forward motion is the result of the orientation of the propellers, which, in the case of an airplane, is such that the vector normal to the plane of the propellers is pointing in the desired direction of flight. In helicopters, the normal to the plane of the propellers is pointing upwards, which permits vertical takeoff. In both propellers and in jet engines, air is being accelerated.
The change in air velocity results in a change of air momentum, which is proportional to the mass and the change in velocity. Since momentum is conserved in principle, the airplane experiences a force that moves the airplane forward, the propulsion force. The strength of the propulsion force depends on the accelerated mass and the velocity difference.
When an airplane rises in the air, its potential energy increases and it therefore requires propulsion. When an airplane accelerates, its kinetic energy increases and likewise it requires propulsion.
The law of energy conservation asserts that potential energy difference equals negative kinetic energy difference minus work to overcome drag plus propulsion work.
A sailplane can find and maintain a constant velocity by diving, whereby its potential energy loss balances the work to overcome drag without the need for propulsion.
If a force acts on a beam at some distance from the fulcrum, a moment of force is generated and the beam starts to rotate.
If the described moment is counteracted by a smaller force at the same distance in the opposite direction from the fulcrum, the resulting moment is lower. In any case, the beam again starts to rotate. For each counteracting force, there is exactly one distance from the fulcrum for the generation of a moment of the same magnitude and opposite direction as the original one to balance the beam. If both forces are acting on the same side of the fulcrum, they have to be oriented in opposite directions. Obviously, the distance has to be selected appropriately to balance the beam. If the moments are balanced in respect to the fulcrum, the forces may be added in the following way. The magnitude of the smaller force is subtracted from the magnitude of the larger force. The resultant force is oriented in the direction of the larger force, and the line of action passes the fulcrum. An airplane that moves freely in the air will always roll around its center of gravity when unbalanced forces act upon it, generating moments. Here, lift is of particular interest. In level flight, lift acts on the wings upon a point around the middle of the fuselage. If, in level flight, the center of gravity at which the airplane weight acts is found at a location behind this position, a moment will be produced which will turn the nose of the airplane upwards. By contrast, if the location at which the weight acts is forward from that at which lift acts, the exact opposite will happen, and the nose of the airplane will turn downwards. So, in order for the airplane to be able to follow a stable, straight flying path, the moment just described needs to be compensated by the so-called horizontal tail plane, which is the wing-like lifting surface below the tail of the aeroplane. The function of the horizontal tail plane is to produce a downforce or negative lift when the airplane nose descends. The downward pointing force is substantially smaller than the lift, since the vector sum of lift and downforce needs to be equal with the weight of the airplane. Since the distance between the point of application of the downforce on the horizontal tail plane is substantially larger than the distance between the center of gravity and the point of application of the lift, the two moments are equal and opposite, and cancel each other out, and the airplane is rotated neither upwards nor downwards.
Generally, the effect of propulsion engines needs to be included in the considerations. As you can see here, the propulsion forces produce a moment that tends to move the nose of the airplane upwards. The horizontal tail plane is relieved. Here you can see a summary of the 4 resultant forces acting on an airplane at level flight.
When the airfoil is placed at an increasingly larger angle of attack against the oncoming flow, lift starts to grow. When the angle of attack exceeds a critical value of around 15 degrees, flow separates from the surface and the lift force becomes smaller. At even higher values of angle of attack, the airfoil stalls and all lift is lost.
These effects are also true for non-aerodynamically shaped flat plates. At small angle of attack values of up to 9 degrees, even thin plates can produce useful lift. The art of manufacturing a good wing consists of, amongst other factors, achieving the highest possible angle of attack without the flow separating from the airfoil surface. Modern wings can be placed at up to about 15 degrees to the oncoming flow. This is the reason why commercial airport runways need to be long enough, since commercial airplanes are not allowed to exceed this value because they would not be controllable beyond it.
The situation is different with fighter airplanes, which can take off from relatively short runways. Furthermore, so-called high-lift devices at the leading edge of an airplane wing, such as slats, permit increasing angles of attack without separation or a catastrophic stall occurring. With increasing angles of attack, the position of the wing in respect to the flow is changed, and consequently, the drag increases.
Vertical tailplanes are based on symmetrical airfoils. If an airplane moves straight forward in the air, the forces due to pressure on the right and left-hand side are equal and cancel each other out.
When the airplane starts to yaw, probably due to a gust, the angle of attack against the flow is changed. As a result, a force occurs, generating a moment with the distance to the center of gravity. This moment rotates the airplane back into its original flight direction.